Okay, so let's start asking if anybody wish to make the 5 minute, 10 minute presentation of why the person is interested in Tomita Takesaki. I didn't get any email and nobody told me if anything going on that direction on Slack. So last chance if you want to share your interest and what brings you uh, to be interested into this mini course, you are most welcome. Okay, if that's not the case, the invitation is still open to tomorrow and Thursday. So if you wish to uh, share like basically a paper or like explain why, like shortly, why you are interested and how it connects to your research, again, please write to me. I will be happy to give you 5 to 10 minutes in the beginning of the lecture tomorrow to answer that question. So today I will start with a question somebody put on Slack, which maybe I gave the false impression that it was easy. So let me just put some space in between the answer and where I stopped. So the person mentioned like, oh, it would be nice to see why the like having a partial isometry. Yeah, so that's by definition a partial isometry is well, an operator in my Hilbert space satisfying some properties, namely, I wish like U. I will reduce notation. Yeah, so it's U go from the Hilbert space to the Hilbert space, and I want the U star U is a projection. Okay, so here maybe just to, because today it will probably be important. By a projection here, I just mean something that the square is equal to the transformation itself. Yeah, so that's uh, so projection is an operator P such that P square equals to P. And not necessarily means orthogonal projection, but here that's automatic, yeah, because U star U is self-adjoint, which means just for free you have that the U star U is a projection. And maybe I give the false impression uh, that if you have like the projection or a partial isometry, I mentioned that if U is a partial isometry, U star is also a partial isometry, and so that means basically the following. So let me just write here. So U is a partial isometry. That means this thing. And I mentioned that this implies that U star is a partial isometry, which of course means that U star star, which is U, is a projection. And the person in the Slack asked because that was not that easy to see. And I do agree, it's not easy to see. I hope I don't give you the false impression that it was obvious that it's true, but it is true. And allow me, like since somebody asked it, allow me to show why is that the case. So the first thing I would like to notice is that U of any vector x square, just by definition, is, well, U square, oh, sorry, it's the inner product of between ux with ux, which is just U star ux x. But because U is a partial isometry, we know that U star U is a projection, which means this thing here is the same as U star U square x, just because the operator is the same. Yeah, so that this operator is a projection, is the same thing as U star U square is equal to U star U. Yeah, so that's my definition of projection. As I mentioned here, the definition of orthogonal projection and projection will not show up because U star U is automatically self-adjoint. So it is a projection, but in particular is orthogonal projection. Or more specifically, it's orthogonal projection. Okay, but then what I get from here is that, so if I redistribute things, yeah, so this is U star U, U star U X, X, which is, of course, the norm square. Yeah, so that's basically passing this operator to the other side, U star U X square. Okay, so the norm of Ux and the norm of U star Ux is the same for all x in my Hilbert space. Okay, so I will use that in my favor to look what happens if I look towards the norm of Ux minus U star U in X. Yeah, so basically I'm conjugating my U star with U on both sides. And well, one thing that I can do is just put the U in evidence. Yeah, so this is U minus 1 minus U star U in X. But I just learned it in the previous formula that if you have U applied to some vector, namely this one, the norm is the same if I put an extra U star. Yeah, so that's what's written above. Yeah, get any vector, if you have a U in front, get any vector, if it has a U in front, you can put an extra U star and it doesn't change the norm. So that's what I'm about to do. So I put an extra star and repeat the vector. Okay, but now I hope you all see what happened. So you have that U star U minus, and here you have U star U square applied to X. But this thing here is exactly, well, because U star U is a projection, this is the zero operator, so this is zero. So that implies that U is equal to U star U. Okay, so that's a consequence of U being a partial isometry. And from that, you also get what U star is. It's U star U star. Yeah, just taking stars on both sides. Okay, now I can try to check what is now U star by using this formula. And then this is, so I did a calculation before just to be sure that I'm not doing any crazy thing. Now I think that I'm doing the right thing. So it's U in U star, and U star I just write 1 second ago, U star. Yeah, so I just plug it U star in here. And as we can see, this is U star square. Okay, so that basically finishes my proof, even though I have never really stated any theorem. But that's just to say, oh, if U star U is a projection, U star is also a projection. And again, since U star U and U star are self-adjoint, they are automatically orthogonal projections. Okay? But as you see, even though it's not too complicated, yes, just kind of a calculation, it's also not obvious. It's not something that you just look and say, oh, clearly, if U is a partial isometry, U star is also a partial isometry. Yeah, that's not the case. Okay? So I hope to have clarified, and I hope to have also showed you that those things are kind of nice. It's not obvious that some kind of, well, properties which are also not too complicated, but they give you important information that's kind of hidden in the algebra. Okay, now going back to our well, the point we stopped at the last well, yesterday. Yeah. we were looking to what would be the desired properties of something that I will call a local net of von Neumann algebras. And what I was trying to do, I hope I have convinced you, is to say, oh, if I want to talk about, well, quantum field theory, or more specifically, algebraic quantum field theory, but even before, if I'm talking about um, quantum mechanics, I will need to talk about C-star algebras, some of the properties just because of convenience, but I was required to have some observable structure, meaning I would have to have like an algebra with sum of operators, with multiplication by scalars. I would have to have an adjoint, in particular because I want to talk about real imaginary parts, and I know that my operators or my observables can only have um, real spectrum just because we just observe real values. And therefore, I would like to also have a spectral theorem. And for that, I need in particular an involution. I would have to require some kind of topology. I would like to have like tell what's an operator converging to another one. And of course, having observables is not enough. You need the states. So the states are the lens throughout we observe the universe. You need to have a state. Otherwise, observables are just abstract objects. So nobody is walking in the streets and say, "Oh, here, a self-adjoint observable. Self-adjoint operator." So you need the state to really obtain something uh, that you can talk about experiments in real life. So the states are the lens we use to really see basically what happens to the observables. And for that, I have to have convinced you that we need at least a structure of a C-star algebra. And for that, I can restrict myself only to algebras which are represented into some bounded operators of a Hilbert space. Also, I hope I have convinced you that I would need a little bit more, namely, I will need unbounded operators, but those unbounded operators will be related to the bounded ones somehow. Position is an unbounded operator, so that's we hope the spectrum, for example, if a free particle, we hope that the spectrum of my position operator to be the whole real line, for example, in one dimension. So it's definitely an unbounded operator. But I also hope that I can kind of box in the particles. So I can say, oh yeah, so if I put the particle in a box, I can put my spectrum just into a bounded region, and therefore you have also bounded operators, and those bounded operators should be enough to recover the bounds. So later we are going, well, I'm not going to go into much detail into that, so that would be these affiliated operators. And then I have say, oh, it would also be very nice if we can look to these von Neumann algebras. I mentioned that von Neumann algebras, they have like, well, more than one characterization. It's the very famous theorem by von Neumann. So represented, so a concrete C-star algebra is a von Neumann algebra. It's equal, if it equals, it's bicommutant. But it also means that it's closed with strong or weak operator topologies. So rephrase Araki, so one of the big names into algebraic quantum field theory, operator algebras, and Tomita Takesaki Modular theory, saying that like the topology induced by the states is the physical topology. So Araki would call this weak topology the physical topology, because when you are talking about convergence of observables, you are in fact interested in when what you really observe converges. And what you really observe is something that has to do with a state, not only with even though the name observable is in the operator, for observing you need the state. So that basically means that so an operator converges weakly to another, a sequence of operators converge weakly to another, if all the expected values for all states converge, or more generally for all functionals, bounded functionals. Okay, but then we were trying to add one more information, and that's relevant, namely, we want to talk about space-time structure. So here I'm doing more free theory, not only because it's the easiest one, but also because it's basically the only one we can really know how to do. Um, so for every region of my Minkowski spacetime, I can associate some algebra that will be related to the observables, right? So I can basically say, oh, my theory has to tell me, yeah, so that was the philosophy of matrix mechanics. The theory has to tell me what are the observables. So the observables should be some kind of set of self-adjoint operators, and I can form the C-star algebra related to those observables. And I can talk about the things that I can observable within a region O1 and also O2. And if they are contained, the algebras should be contained. If they are causally separated, the algebra should commute. I hope that I can implement my or proper autochronous Poincare group by unitaries, just as I'm saying, like the algebra of some region O. When I act with these unitaries associated to the Poincare group, they act basically by transforming the region O into the region G of O, so they act geometrically. And I hope to have a vacuum. So again, I'm talking about vacuum representation here. So there exists a normalized vector that we'll call omega, which is invariant by the Poincare group. And if you take the algebra of the whole space acting to the vacuum, it approximates any vector in my Hilbert space. So for the physicists, I can say, okay, it approximates all the states, even though states we define it in a different way. I want to have a spectral condition. That means that the generators of these space-time translations, we have some property. And here I just saying it will say the same thing as saying that H, so the Hamiltonian, is positive. Okay, so that's not a precise statement, but just I will, as I mentioned, I would like to show you the idea behind Heschlida, and that will be important. So for now, think about H to be positive. Yeah, so that's one of the things that came out of that. Yeah, and one last thing, which is called weak additivity. So my question is, what happens if I have the algebra of a union of regions, or maybe J is a better letter, and I want it to be equal to the algebra generated. So that's this is the notion of the smallest C-star algebra generated by all of them. Yeah, here not only finite, so we can have infinite ones also. Yeah, so basically, what I obtain if I look to the big region is not contained kind of in the boundary. Yeah, so that's basically I can re-obtain the information by composing the local observables. I can obtain something in the union. Okay, so why I mention you that, not only to know, so this is some of the requirements we can put to defining a local net or something that would be a quantum field theory. There are many more, so I'm not claiming this exhaustive list. But the interesting result that comes out of that is the so-called Heschlida theorem that will be a very important motivation to what I'm going to talk about. Hey, oops, why what? And what does this theorem say? So it says that if you have a net of local algebras, that'd be a local net. So that's fine. The previous axioms. Then if I look to the algebra of any region, doesn't matter how small the region is, and act with this algebra into the vacuum and take the closure, it gives me the whole Hilbert space for any region. So you can say, oh, but you have assumed that some algebra will give you the whole Hilbert space. And that's true, but I have assumed that the algebra for the whole Minkowski space would give my Hilbert space after taking the closure. And here I am assuming that just a bounded region doesn't matter how small it is. Yeah, so it only have to be an open set. Yeah, um, uh, containing. Yeah, so that's only need to have like an open region inside this region O. Yeah, so if it's just a point, it's likely there is nothing to a point. Yeah, so I'm thinking about regions which are reasonable, let's say. Okay. Okay, so why is that true? So how can it be? And again, okay, it's a proof. I will not go into again full detail, but I would like to also something in the chat. Again, the last part, please. Can you just precise which was the last part? So only the like about the statement of the theorem, or what I mean by weak additivity, or so the closure. Oops. So here, yeah. So what I'm looking here are so this set just to try to clarify everything. What I'm meaning by this set is basically the set of all A applied into omega when A belongs to the algebra A of O. Yeah, so this is basically you have this one vector that I assume it to exist. Yeah, so that's the vacuum vector. And here I'm taking an operator which comes from my local algebra. So like it's not necessarily an observable because it can be a non-self-adjoint operator, or not even unobservable, even though if it's self-adjoint. But if you act with uh, this operator that comes from the algebra of things that I can locally observe into O, so this gives me a subset of my Hilbert space. And what I'm claiming is that this set is dense. Yeah, so that's if you take the closure of this set, it's the whole Hilbert space. That means that any vector in my Hilbert space can be approximated by vectors of this type, by local observables or local operators, let's say, acting into the vacuum. Yeah, so what I was stressing was the difference between the assumption that I said in here. So this is an assumption that the vacuum, it is cyclic. So these properties mean cyclic. Uh, for the algebra, when you take the whole Minkowski space, which means the things are not local. Yeah, so I can get like observables which are kind of supported into the whole Minkowski space. Yeah, so that's not necessarily into a small region. So it has to be the whole space. And that sounds more reasonable because, well, my intuition is so the vacuum, if I act but with operators kind of localize it anywhere, which means in some sense non-localize it, yeah, because it's localized in the whole Minkowski space means non-localized, yeah, so that's they can be arbitrarily dislocalized. Then I can generate almost any vector in my Hilbert space, so basically almost any state by acting into the vacuum. Yeah, so basically, I say any state can be constructed by non-local uh, procedures, yeah, so non-local steps acting into the vacuum. Here, I'm saying something much stronger. I'm saying that for any region O is not only the whole Minkowski space, this is also true, which is very counterintuitive. And allow me to try to make this kind of like a anecdote or to stress how significant the result is. I'm telling you that if you have the vacuum state, only with local actions into my desk or in the palm of my hand, just doing local operations in the palm of my hand, I can generate any state or approximately any state in the galaxy of Andromeda. So that's basically what this theorem says. So that's very counterintuitive. And originally, when it was proved, people thought it was wrong. Yeah, so this does not corroborate with intuition. And I'm again having problems with the chat. So sometimes it opens, sometimes I just get some blank uh, window. So I will keep going a little and then I will check again if I can redo. Oh, now I can. Uh, yeah, nice. Okay. Yeah, so originally people thought it was wrong. Yeah, so it cannot be true. It's too counterintuitive. But later, more and more results corroborated to the Heschlida, and now it's, I would say, widely accepted. I think nobody will really discuss it. And one thing that comes out of that, so the consequence or the upshot from the physical intuition is the vacuum has very non-local properties, or some would say that the vacuum has like is different regions are too correlated. And that's very similar to what happens if you basically deal with Gaussians. So I can also just dealing with Gaussians into a small interval. Yeah, so it's if you get Gaussians, but the mean f, the value of the Gaussian is into a small interval. And with that, I can also generate it basically almost any function. And the reason is because you can basically subtract these two and kind of like the differences in the tail of the Gaussian are relevant. And then you can, well, it's smartly, but basically it's mathematically um, using that fact to kind of annihilate what happens into a small, like my local region, and generate an effect which is far away from me just because of this effect of summing up the tails of the Gaussians. So that's almost what's happening here from the intuitive point. Yeah. So the vacuum has this kind of like strange correlation. So it's has well, let's say entanglement properties, just to use some kind of buzzword, in such a way that only with local properties, so with properties which is in a very small region, I can create effects even outside my region. Yeah, or even much far from my region. Yeah, so it's just in the palm of my hand I can create any state or approximated any state in my Hilbert space. And just one final point is like by disclosure is just the closure in the Hilbert space, yeah, because it's okay. So the algebra has its own topology, but when I apply the elements of the algebra in the vector, it gives me something in my Hilbert space. So it's a subset of my Hilbert space. And here I'm just using the Hilbert space norm. Yeah, so that's the whole point. So let's see something more in the chat. Is it still valid in expanding universe like the Seater? Good question. I don't know so of many uh, generalizations. So there are other versions of Heschlida which work in more generality. I think in the Seater, yes, it's also true. And the point is that you are going to see, like I'm going to give some kind of idea of the proof. It relies on the um, on analytic properties. So basically, spaces when you can copy it, it would work. Of course, it will rely on all these axioms, or at least in the vast majority of these axioms. For example, you have to put some kind of spectral condition, and which I'm not really sure how physical they are in the sitter, but I would expect that some version adapted would hold in the sitter. Yeah, so it's again here, for example, the group will not be the same group. Yeah, so it's not Poincaré because you have different symmetry groups. As I mentioned, here it's very fit to free field, so I'm using Minkowski space, so that gives me the advantage of having a very clear group, which I'm implemented by unitaries. So if you change the space-time to something different, you have to also change the group of symmetries. Yeah, so that's so my group will not be Poincaré anymore, and there is no general theory that deals with like curved space-times in generality. Uh, I I have to say I cannot really point out to a reference, but I would say that yes, it's in the sitter a similar result should hold choosing correctly the axioms, but I'm not aware of the precise reference. Okay, so how does the idea of the proof, at least I would prove, but it will be a little bit of a sketch because of time constraints. So the whole thing goes with looking to what happens if you take any vector and an operator acting into the vacuum, and that should be zero. So that's basically what happens if you have a vector psi which lives into the orthogonal of this set. Yeah. So I'm supposing here that psi lives into a O omega orthogonal. Yeah. So that's the definition of being the orthogonal. And what I want to prove is that psi is the null vector, meaning there is nothing that is in the orthogonal of this set, which means the set is dense. Yeah, so that's the strategy of the proof. Yeah, so get a vector phi, which is into the orthogonal and prove that the vector is zero. Okay? Okay, so in particular, I can take the vector, this A's to be the product of fields. So I'm taking my A to be of the form phi of some Hn with some function supported in in the region I'm interested in. Okay, let me just go with some dots phi of H1 acting to the vacuum, and that should be zero. Yeah, so those are, so I'm taking here for all phi hj in a O. Yeah, so if you take fields which are in my local region, I should have something, well, which gives me zero. Yeah, just because I'm supposing it is in the orthogonal. Now, look what's going on. Yeah, so my region O has an open uh, region inside. So where is the here? It's a straight line. Yeah, so my drawing skills are like, let's say, not so good. So I'm taking advantage of the computer. Yeah, so something in the chat. Okay, again, I'm having problems with like loading the chat, but it will probably work in a second. Yeah. Okay, yes. Okay, so suppose my region O is just this blue region in here. This is my O. How can I go back here? And then I can inside, so allow me to change a little. So suppose my region O is some region in here. So let's just make it smooth. So this is, the whole thing here is O. Yeah, so that's if it's not the O, remember O has some open region inside, I can just restrict it to this open region and I'm happy with only the open region inside O. Okay, now I can just get some smaller region inside region O in such a way, so this is my O2, in such a way that I can go a little bit to the right or to the without leaving the region O. Yeah, so this is my epsilon. Yeah, so I can go epsilon to the right or epsilon to the left without leaving my region. Where's the white here? Okay, so what do I obtain with that? That tells me that if I look to psi of phi hn, but then I have, well, the last one or the previous last one, 2, and in the very last I put some U, and U, remember, is the generator of my translation, so it's a horrible calligraphy. So X phi H1 U, and then I have the U star, but U star is U of minus X, yeah, so that's a one parameter group. In omega, that should be 0 as far as my U is acting only with parameter X is smaller than epsilon. Sorry, it's wrote O in here, it's X. Yeah, so my region I'm picking one dimensional just because it's easier to visualize. So you have the region O, you have a small region O tilde, and you can go a little to the left or to the right, or like go a little around in any direction if you go in more directions with your region O tilde without leaving the region O. But I know that if I act just with operators which live inside my region O, I'm like safe. Yeah, so I don't leave the region O, which means so this inner product should be 0 for all phi h j in a O tilde. So I'm restricting even more. Yeah, so before it was for all phi which lives in the region O, and now I'm taking phi's which lives in the region O tilde, and the modulus of X is smaller than epsilon. Okay, so I don't in fact need all of them to be in O tilde, I just need the very last one to be in O tilde, meaning all the others are in the region O, yeah, so are operators which are localized in the region O, and the last one is in the region O tilde, but then I can move it a little around with my unitary, which acts geometrically. So remember that if I so I'm using this notation with phi and fields just because I think it will be more like user-friendly, yeah? So that would be more approaching to the physicists, but you can just write any operator A, yeah? So that's not the important point. But so just visualize that since U acts geometrically and this guy here, so this phi of H1 lives into the region O tilde, by acting with the unitary that gives translations, since it does not, since U acts geometrically, if I act with like some X such that the modulus is smaller than X, I will not leave my region O. Yeah, I will leave the region O tilde, but not O. And that means that this is true. Yeah, so that's this inner product is 0 for all X. Okay, so now the trick comes in. So allow me to now look into what's happening not in the space-time region, but in this parameter X again, even though the name is the same. Yeah, so here I have my X. Oh, sorry, my X. I'm not looking now to the region. So this is the region. So I'm looking here now to what happens with the parameter epsilon or the parameter X. And within the parameter X, what I learned is if I move this parameter x between minus epsilon and epsilon, the inner product vanishes. Yeah, so that's the region I know that this inner product vanishes for this parameter x. Yeah, so if I use the parameter x into this region, I have 0. Okay, now allow me to also look to the imaginary part. So up to now, of course, I'm only thinking about my parameter group with real parameter, but I can also look to some imaginary part of x. And one can ask, okay, but why is it possible to have this analytic extension? So where does it come from? And the answer for that is that this u is, well, it has a generator. So u of x is nothing but e to I h x. And remember that I have some spectral condition, and I just told you like, okay, for now, imagine that this spectral condition means that h is positive. The true condition is that the joint spectrum of the translations, the time spatial translations, lives into the positive cone. Yeah, so that basically tells you that times move forward, and you cannot have like translations that go flat. Yeah. Okay. So, or not translations that go faster, but one cannot go faster than light. So that's the general situation. So here I'm just doing some kind of simplification just to make it like more understandable. But either you look to some like a region, like some the positive cone into Minkowski, or you here just say one dimension and it just means that the Hamiltonian is positive. That means because of spectral calculus that I can extend this operator u of x. Yeah, so remember that u of x just being equals to e to I h x. I can just represent it using spectral calculus as the integral of e I lambda x d e h lambda. Yeah, so my spectral measure. And since h is positive, that goes from 0 to infinity. Yeah, so that's my generator can be unbounded, but I'm saying it's bounded from below is enough. Yeah, so but okay, so bounded from below, just set the below to be 0. That means that this exponential here can be extended to lambda in the upper half plane. Why? Because if lambda is of the form iy, with this extra I get a minus. So it's e to minus lambda x. And remember that I'm integrating from lambda from 0 to infinity. So, sorry, my mistake. So it's not lambda that's ix, it's x, which is of the form I something, sorry. X is of the form I some y, or like I can just say real of x. Then again, so the I together with this x, you get a minus, but since I'm integrating from 0 to infinity, so if the real part is positive with this extra I, what I'll get is minus lambda x, but the nx are positive, which means that this exponential will be just exponential of minus the real part of x times lambda, and that is integrable from 0 to infinity. So that's important. So in the upper half plane, I can extend the action of u analytically. Oops. Yeah, so this u extends analytically in the upper half plane due to my spectral condition. Okay, so now I have, where is it? I'm always probably to change the color. So I have my real part of x, I have my imaginary part of x. I know that my function vanishes in between minus epsilon, and it's analytic in the upper half plane. Very good, but then I can use Schwartz reflection principle. I can just define um, a new function in the lower part, namely g of z, which is just f of z bar bar. Yeah, so here I have my function f of z, and just to tell you what's f of z, since I never really wrote that down, is precisely this thing. Here, I'll try to copy. So this is my f of z. So now z is complex. Oops. Z. I have another one in here. And well, okay, so one point is that what we know about omega, well, it's invariant by the Poincare group, which means that this thing here is just omega. Yeah, so that's just a simplification, will not play any big role for now, but that's some important fact. Yeah, so that's basically I'm looking to this function. And what I learned is this function f vanishes in this interval. It's analytic in the upper half plane. And I can look to this g of z, which is the conjugate of the conjugate parameter into the lower half plane. And this function will be also analytic. Yeah, so this is it's called well, Schwartz reflection principle, or well, that's part of the Schwartz reflection principle. So this function is analytic into the lower half plane. Okay, but then again, as part of the Schwartz reflection principle, or in more generality, something that's called the edge of the wedge theorem tells you that if you have a function which is analytic in one region, analytic in another region, such that the boundary is a curve, and the function is continuous in these two regions, including the boundary, and the two analytic functions coincide in the boundary, then the function is analytic also in the boundary. Okay, so that's exactly the type of situation I have in here. I have a function that's analytic into the upper half plane, it's analytic into the lower half plane, and they coincide into this green region in which the function vanishes, yeah, because it's just look to the function, it's just given by the conjugate of the parameter conjugate, but the conjugate of 0 is 0, and in the real line, the conjugate of z is z, yeah, so that's into this region, the green region, the function defined above, so f of z and g of z coincide. So what we have is a function which is continuous, analytic into the upper half plane. You have the function d, which is analytic into the lower half plane, and the two functions coincide into the boundary, and they are continuous into this boundary. Therefore, the function is also analytic into this gray region. Yeah. So in this situation, the way I wrote it, I can just call the Schwartz reflection principle. As I mentioned, with more generality, if you are really dealing with the positive cone and so on, you have to use what's called the edge of the wedge, which is a more general version of the same theorem. The proof is not too complicated. I'm not going to go into the details, but basically go to using Cauchy formula. You can go with some upper circling here. Yeah, so you integrate in here, and you integrate into the lower region, and or maybe the opposite direction. Oops. So what you see is that thanks to the Cauchy theorem, the function into this dot that I put in the middle is equal to the integral in the boundary for both boundaries, and I can just make this dot go like converge to the line. So when the two dots converge to the line, they coincide. But then what we see is that you have the integral on the upper part of the circle, you have the integral on the lower part of the circle, and the integral into these two lines. Yeah, so these two lines. So by the lines, what I mean is these two lines. But as you see, they are integrated into different directions and they give the same integral because, well, the function is continuous. So therefore, they will cancel out and you will conclude that the value of the function into the center is equal to the integral into the circle, which is basically Moreira's theorem, which tells you that the function will be analytic. Vamos pensar. Yeah, so I will not call it a polar decomposition, but the answer is yes. So sorry, maybe I should just have read the question. So somebody asked me if this decomposition of u as this integral the way I wrote just follow from spectral calculus. Yeah, so what he called polar is because this here is just phase. So again, I should just not call it polar decomposition, but I do agree with the question you indirectly posed that yes. So what I'm saying is like since U is supposed to be a unitary operator, in spectral calculus, you see that the spectrum should lie into the boundary, yeah, so into the unit circle. And since the spectrum should lie into the unit circle, and you can represent any normal operator U as the integral of the over the spectrum with the spectral measure, this decomposition just follows. So this thing here is spectral theorem. You can say either for normal operators, can also be for, well, if you transform it, you can get a self-adjoint out of the scalar transformation that I mentioned. But then it follows from the spectral theorem and the fact that U is unitary. Okay, so what we learned with this again, probably just think, but I will check again if there is any follow-up question. Yeah. Okay, so what we learned with this small argument with these two sum circles, which have dots that converge to the real line, is that Moreira's theorem will tell us that the function is analytic. So that's basically how you prove Schwarz reflection principle, as I mentioned, more generally, the edge of the wedge. Okay, but now I have a function. So this function, which is defined in the whole blue area, which is defined by f of z into the upper half plane. It's defined as g of z into the lower half plane. They are both analytic, and I also learned now that it's analytic in the boundary. Okay, but then I have a function which is analytic into this whole blue area, including the green line, and in the green line it vanishes. Well, but if you have an analytic function that vanishes into any point which is an accumulation point, yeah, so it vanishes in any set which has an accumulation point where the function is also analytic and vanishes, then the whole function vanishes. Yeah, so that means that into this whole region, so allow me to now drop the dark blue into this line. So into this whole blue region, including this line, the function vanishes. But if the function vanishes into this whole blue line, blue region, so the only part that's out is the white part, yeah, so the white piece of real line that is out, but the function f is analytic in the, it's continuous in the real line, well, then there is not much that remains to happen. So the function f of z, so that implies, right here. So that implies that f of z is 0 into the whole real complex plane. Okay, but let's see how this thing started. So I look to some region O tilde, and then I have my vector psi, and this vector psi is orthogonal to everything in the region A of O. But then I plug this U of X, which allows me to go a little bit with the last, like the support or the region where the last operator lives. But now I just learned that I don't need to restrict myself with only a translation of size epsilon. I can in fact take any translation and it will be zero. So that means that in fact I can get this phi, or after conjugating with u, in any possible local region that's basically delocated, or like just shifting the region O tilde. Okay, but then that's basically everything, yeah, because I can just get any O tilde and I can just delocate or shift it to whatever. And I can just get unions of small regions that like I can just get by shifting O tilde, or even small regions than O tilde, and I can cover any possible region. More than that, I can go one step further and just look, let's say, to some F2 of Z and just go with psi phi of Hn, phi, and now I stop in H3. And then I put an extra U, and now, well, just to not, okay, I will go with this one. Uh, Phi, oh, sorry. Yes, so phi of H2. And here, remember the last, oh, sorry, I forgot just the last one. Z, U of minus Z. And my space is not enough. So the main difficulty here is to prepare to the big formulas that show up. Okay, yeah. So this last vector here is phi of H1 acting to the vacuum. Yeah, so here I just learned that this phi don't need to be localized anymore. Yeah, I can just put it in whatever region. And because of weak additivity, if I get any region, doesn't matter if it's O or not, I can just get a small region O tilde and shift it, or getting an even smaller region inside O tilde and shift it inside this given region, and just sum up very small pieces in such a way that the union gives this given region. And thanks to weak additivity, I just conclude that the algebra of this given region coincides with the algebra given by the union of these very small pieces that I got by shifting O tilde or something smaller. And into this whole algebra, the whole, like when I act with phi in omega and I put other phi's in front, I always get zero. Okay, but now I can interact my argument and put some u of z into the second operator now. Yeah, not in phi 1, but in phi 2. This guy here will not bring any trouble because that will just shift the region of phi. But shifting the region of phi will have zero effect. I just learned that I don't care about shifting phi. It will just remain the same. Yeah, I can just artificially put a u of z in here just to see if it's some phi that's delocated. In any way, I will do exactly the same argument, but now with my u applied into the second vector. Yeah, so in between the second operator and the vacuum. And I will get exactly the same conclusion. And by doing that any times, what I will learn is that psi, if I get any vectors Hn phi H1 in the vacuum, it will always be zero for all phi, oh, sorry, phi of Hj, the way I wrote, in any possible region. So if it's in any possible region, it's in the whole Minkowski spacetime because of weak additivity. Well, but now this set of vectors, this is dense. Yeah, because of my assumption. Yeah, so that's I suppose that like for this set, the vacuum was cyclic. Well, but then that implies that psi is zero. So you see, the crucial point here was an analytic argument that allows me to shift my region O to any possible region. Yeah, so that's you start with a small one, and out of this small one, I can use the analytic argument, which is only true because of the spectral condition, to shift my vector for whatever region I have. Okay? So again, counterintuitive. So this argument you can find, for example, into this paper by Edward Witten. So it's written in there, so you can also check and see how he explains and get a little bit more usage with, as I mentioned, a little counterintuitive. But you see, it's basically about implementation of the translations by unitaries, a spectrum condition, and weak additivity. So that's basically what I use it. And the fact that if I get the whole algebra into the vacuum, it's dense. So that's what I use it. Okay. But now let's just jump over. This was just the answer of the question in the beginning. Okay. So allow me to just make a small drawing just to convince you of something quite interesting. What happens now if I look to the commutant of O? Yeah, so look how interesting we have. So if you now I'm just giving a space-time diagram, and I'm drawing well, I like to draw wedges. So allow me to draw a wedge in here, another wedge in here. So that will be my region O. And of course, I can look to some region which is not into the, which is causally separated from O. So, so that will be, yeah, so for example, something in here. Yeah, so that's the two are causally separated, and both regions O and O prime have open interior, the way I drawing. Yeah? So they are just obtained by intersecting some wedges. So remember that thanks to one of the conditions, so the Einstein locality, in fact, we know that the algebra for the region O prime is contained in the algebra, in the commutant of the algebra O. And that means that this region O prime and the region O are both cyclic. So by cyclic, I mean that if you take A acting into the vacuum and you take the closure, it's the Hilbert space. But if you take O prime acting into omega and you take the closure, it's also the Hilbert space because they are both open regions, allowing that to be true. One known result, or it's not too difficult to prove again, but it's I will, for lack of time, avoid going to further details. It's just messages. Into cyclic vacuum. Yeah, so again, it's this kind of counterintuitive idea that the vacuum has kind of internal correlations. Yeah, so that the vacuum has very non-local properties. So that would be the way of stating. Yeah, so the vacuum is very non-local. Namely, you can generate approximately any state, even outside any state that's not local, just from the vacuum using only local procedures. So if the procedures or the operators that I'm using are local, and I can construct things which are not in my region, is because the vacuum is non-local. And in fact, the vacuum is very non-local. Yeah, so that's would be the physical intuition. And again, counterintuitive. So that's why people resisted a little in the beginning to accept that the vacuum was cyclic. But again, today it's basically accepted by everybody. I don't know anybody who question it. Okay, so what I was about to mention is that if you have the vacuum cyclic for the algebra, but also cyclic for the commutant, yeah, because notice that this set here is smaller than this one, prime bar, and the prime now is out, yeah, so notice that I'm saying that AO prime is contained in the commutant of the region O. Therefore, I have more operators in the commutant than in the region O prime, which means that I have more vectors in the one down, but of course, it's not possible to have more in the closure because it's already the whole Hilbert space. So one consequence is that, like, okay, so the vacuum is cyclic, meaning the algebra, and now I stop talking about the region in omega is the Hilbert space. And then I'll say that the vacuum is also separating. And what means to be separating means that if you have an operator acting to the vacuum and it's zero, is because the operator is zero for all A in my algebra. And one point is that like a vector is separating even only if it's cyclic or cyclic, I never know how to pronounce, to the commutant. Yeah, so being cyclic is of course cyclic for A, for A. Another thing that I cannot get used to is with the proposition. If it's cyclic for A or if it's cyclic with respect to, maybe it's with respect to A, it's maybe better in terms of English. I have no idea. With respect to A, with respect to A, with respect to A. Okay, so we have these two properties, namely that the vacuum is cyclic and separating. And that's the key to define Tomita Takesaki theory. Yeah, so that's so this whole kind of path going through algebraic quantum field theory and defining that is to say cyclic and separating vectors, and cyclic and separating together is called standard. Yeah, so a standard vector is quite fundamental in quantum field theory, or at least in algebraic quantum field theory. So that will be a kind of a cornerstone for built-in Tomita Takesaki modular theory. And what I try to, well, not only to kind of give you some idea what is algebraic quantum field about, I hope also it helps understanding the seminars in the event next week, but it will also motivate why Tomita Takesaki and why it's a very physical situation. I'm not creating crazy mathematics that has no physical application, quite the opposite. And again, allow me to, so I hope I tell it every day, to show you that the physics is the mathematically pathological situation. Yeah, so you see, out of the like very reasonable physical assumptions that I had in here for my local net, I end up constructing some vector which is cyclic and separating, even though it's very counterintuitive. And from that, I can construct an even more powerful theory that may be even more counterintuitive, but it's very helpful. Yeah, so allow me to mention a paper by Borges called Revolutionizing Quantum Field Theory with Tomita Takesaki Modular Theory. So it's a paper published, I think, in 2000, which worth checking. So since 2000 at least, the community in Tomita Takesaki were very aware of the importance of this theory for algebraic quantum field theory, and very many results. And it will be clear by tomorrow when I talk about Tomita operate or Tomita Takesaki theorem, why is that so important. But for now, allow me to just go naively in trying to convince you how important those things are, and I will be a little bit biased into that direction. I will use what is called a standard subspace, but here I will always make a very clear connection with von Neumann algebras because probably it's the situation you are more familiar with. But let me advertise these standard subspaces, which are something that are getting more and more attention, and well, you are going to understand. So what I learned is that my sister algebra, and allow me to now, okay, at some point I will have to make a shift and go to a von Neumann algebra. But if I have my sister algebra, so any operator in here, in here can be written as the sum of two self-adjoint ones. We have already discussed that. Yeah, so that's the real part of A plus the imaginary part of A. And what's the real part is just A plus A star over 2. And what's the imaginary part? So maybe just make it clear that it's the I is out. So it's A minus A star over 2I. And well, that's it. Okay, then what I learned is the following. So since my vacuum is cyclic for my algebra, I can also say the following. So A in omega is equal to, well, the real part of A in omega plus the imaginary, or plus I, the imaginary part of A in omega. And I can look to this space instead of looking to the whole set of all operators. I can only look to the self-adjoint ones. So what I'm saying is that I can define a space which I call H, and please notice that my Hilbert space is this calligraphic H, and the straight one will be from now on my what I would call the standard subspace. I can define it as being the set of all vectors of the form A omega in my Hilbert space, where A is in my algebra, but it is self-adjoint. Okay, so not all vectors, but now only self-adjoint ones, and I can take the closure. Oops. Yeah. Okay, so what I learned about this H, it has the following properties. First is a real vector space. Or, well, since I take the closure, is a closed real vector space or a vector subspace. Yeah, so one problem is it's not complex anymore. Even though my Hilbert space is complex, it's not complex anymore. Second thing, H plus IH is cyclic. And what I mean by cyclic, that if you take H plus IH and take the closure, it's a whole Hilbert space. And 3, it has the following property. If you take H with IH, it's separating, or sorry. So H is cyclic, sorry, meaning this is true, and H is separating, meaning this intersection is just a null vector. Okay, this is what I'm going to call a standard subspace. Yeah, so some closed real vector space, which is cyclic and separating, will be called a standard subspace. And what I'm going to just tell you now is that this is exactly the situation for what we just checked the the vector. Yeah, so for the vacuum. That it's cyclic should be easy to see, because if you take A in a vector omega and you take the closure, it should in particular be equal to, well, since the vacuum is closed, so allow me to start with this one. So A in omega closure should be the whole Hilbert space. But what we just saw is that this should be all the self-adjoint ones acting to omega plus I, all the self-adjoint ones acting into omega. But if you take this thing here is contained in H, because H is the closure of the set. So this thing here, oops, is contained into H plus I H bar. Yeah, so that's all self-adjoint operators acting to omega is smaller than the space omega. But of course, it's the closure of something that lives in H, therefore it lives in H. Therefore, you have equality into all the steps. Yeah, so that means that the space that are constructed this way, yeah, so with this definition from the von Neumann algebra, is in fact cyclic or cyclic. Again, I never know. Separating gives you a little bit more trouble. I'm just checking my notes. It's not hard, but if you are not careful, you really easily run into some mistake. So here. Yeah, so here. Sorry. Okay, I lost my notes, which means I will have to do it on the spot. Yeah, so I just lost place in where it's showed. Okay, so one situation is easier. Okay, so if you don't take the closure, cyclicity would be obvious, right? So you have A in omega would be equal to I B in omega. Yeah, so meaning this thing here lives into the algebra self-adjoint acting omega, and this thing here should be something that lives into I times some self-adjoint one. But then since the vacuum, yeah, so if that was true for this buff, that you would conclude that A equals I, B is self-adjoint, and anti-self-adjoint. Adjoint. Just because A is self-adjoint, B is self-adjoint, but then when you multiply by I, it will be self-adjoint. Yeah, so here I'm using the fact that the omega is separating. Yeah, so if you have A omega equals IB omega, that means that A minus IB in omega is 0. But that cannot be, yeah, because, well, that would imply that A equals IB, and that's what I'm using here. But then you cannot have that A is self-adjoint and anti-self-adjoint. Yeah. So for one hand, when you take A star, it should be equals to A. But then when you look to IB, it should be equals to minus IB star. But minus IB star should be equals to minus A star, which tells you that A is 0. So that is the situation which is a little bit easier, but we have to be a little bit more careful because we have the closure into H. So let's see if I can reconstruct the argument. So if you have a vector, allow me to call it H, which lives into H intersected with IH, then I can say that H is the limit when n goes to infinity of a n acting into the vacuum for self-adjoint A's. But it's also equal to the limit when n goes to infinity of I bn omega with bn into a self-adjoint. And let's see if I can generate a problem with that by calculating what is the norm square of H. So let's see. So that should be H with H. And then I will just write that as the limit, and I will use joint continuity, I guess, when n goes to infinity of a n omega I b n omega. Yeah, so this goes to H, this goes to H. The inner product is jointly continuous, so I can just write this way. And now I will just, let's see what I want to do. I probably want to conjugate, so that should be, yes, okay. Let me check. Oh, okay. I just, yeah, the way I did this slightly different way. So here, raising, yeah, there's in here, so some should okay, so I'm not really sure where is it in here. Come on, I had like I took the notes of what it should be. But okay. So how does it go in here? So I can write this way. I can also write it the other way around. So let's see. So first things first, this is a real number. So taking the conjugate should not change it. Yeah, so that's the norm square is real. So the limit, I can just take the complex conjugate in everything, so it should not change the result, which means I can just go with b n omega a n omega. Yeah, but if you look to these two results, one of them is equal to, no, okay, so now I did something wrong. So for not losing too much time, allow me to do this one tomorrow. I should have done I have it somewhere in my notes, and for some reason I cannot find where I wrote it. It's just a small trick when you play with the fact that it has comes from self-adjoint operators, and then you have an I times a self-adjoint operator, and then when you go around with the I's either in the first entry or in the second entry of your inner product, and you get a minus sign, and therefore it cannot be true. Yeah, so that's basically to forces the norm of H to be zero. But allow me to do that tomorrow. I will start with that. Okay, but then what I have is like a closed real subspace of my Hilbert space, which is cyclic and separating. Okay, so that's basically the situation. Yeah, and what I want to play with now is the complex structure of my spaces. Yeah, so either by looking to these standard subspaces, which are only real subspaces of the complex one, or with my algebra. So I will define my Tomita operator, which I will call S0, the following way. So allow me to originally define it into only vectors of the form A acting into omega, which is a dense subset of my Hilbert space, go into my Hilbert space. And for every operator A applied into omega, it associates A star into omega. Okay, what does this operator do? So, well, it takes one vector and associates another vector. But here, one tricky thing may show up is why is this operator well defined? So allow me to put some hypothesis. So let, okay, here, okay, A be a phenomenon algebra. And omega a cyclic, oh, obtained in D of H, a cyclic, and separating vector. Then I can define this operator, which is well defined just because if A omega is equal to another representant of the same vector, so if I can write the vector in two ways, then A has to be equal to B. Yeah, because A omega is separating. Yeah, so the operator is well defined thanks to the fact that there is only one representation of A omega. Yeah, and that's well, that's A omega. Okay, so just for simplifying my life, allow me to check what happens if I look to this S0 into A omega in terms of the real and imaginary parts of my vector A. So if I look to S0 of A, this is the same thing as S0 of the real part of A acting into omega plus I, the imaginary part of A acting into omega. And my result for that should be A star in omega. But what is A star in omega? Well, that's real part of A plus I imaginary part of A star acting to omega. Well, but real part of A is self-adjoint. The I gets a minus sign. And the imaginary part of A is also self-adjoint. Oops. Fighting. So forgot the omega to omega. Okay, so what I'm doing is nothing too complicated. I'm getting something of the form H plus IH, 1 and 2, and I'm getting H1 minus I H2, where, well, H1, the way I defined it above, H1 and H2 belongs to the self-adjoint operators acting into omega, which is contained into what I define as to be my standard subspace. So it very much look like the complex conjugation. Yeah, so you get something of the form real plus I imaginary, and you get real minus I imaginary. So that's not too complicated. And what's the physical meaning of it? Okay, so it's so Pedro also gives some answer for the question. Yeah, okay. Okay, so what I'm doing is not much different from just some vectors. Yeah, so basically, uh, one particular situation that I can have is that if I look to, sorry, I think that's, I just got a message that my connection was unstable. So I hope you haven't lost much. So I will just go two sentences below, or two previous sentences and repeat them. So what I was saying is that this operation is not too different from complex conjugation, but with vectors in a Hilbert space. Yeah, so look kind of a naive type of operation. So one particular example is if, for example, I take my H, so my standard subspace to be, for example, R2, contain it in my Hilbert space, which I would take to be C2. Yeah, so that's one example of a standard subspace, namely a closed real subspace of C2, which is cyclic and separating. Uh, and then I'm just getting pairs of vectors of the form. Oh, sorry. So, okay, originally I was more thinking about this one, but the other one is also true. Uh, and then what I'm basically looking is to um, decomposing things in real and imaginary part. Yeah, so that's in finite dimension, everything is in fact easy to see that Rn is cyclic and separating Cn, that it's separating, it's obvious, and that cyclic is in fact because Rn plus I Rn is in fact the whole Cn because of dimensions. Yeah, so that would be the easiest type of example, but many others are well, exist, in particular when my Hilbert space is infinite dimensional. Okay, so I can define it this way. Here I'm quite of like a looking just to this space that I get from the operators. Yeah, so only from taking the star of an operator. I can also look to another one. Let me call it directly S of H, which is the one that I take H1 plus exactly the same operator, just with a bigger domain. IH2, where H1 and H2 belongs to H. Yeah, so notice that this is a well-defined operation exactly because H is separating. Yeah, so if you have H1 plus IH2 equals to H1 tilde plus IH2 tilde, that implies that H1 minus H1 tilde is equal to I H2 tilde minus H2, which is impossible because this belongs to H and this belongs to IH. Yeah, so that would imply that H1 is equal to H1 tilde and H2 tilde is equal to H2. And therefore, the composition in this way is unique. Yeah, so the operator is well defined. Question, is this operator closed, or is this operator as a zero closed, or if it's not closed, is it closable? And that's what I'm trying to convince you of now. So proposition SH is closed. I read closed, not even closable. And SH is equal to S0 closure. Yeah, so that's the Tomita operator. So this operator is called Tomita operator. So the Tomita operator of the standard subspace is the closure of the Tomita operator. defined only in like for the algebra. So how does it go? And I prefer to do this proof in terms of another operator. Namely, I would like to look to a special projection, which is given by 2sh minus 1. Okay, so the domain is the same. Yeah, so notice that the domain here is important. Yeah, so that's sh is defined from h plus ih into h or into the Hilbert space. Yeah, that's depending how you prefer to look. Okay, and S0 has a smaller domain, as I mentioned here. It's of the form h1 plus h2, but it lives just into uh, the space before taking the closure. Okay, so this one, of course, has the same domain as sh because identity is bounded. And what does this operator do? It takes a vector of the form h1 plus I h2 and gives me h1. Yeah, so it cuts out the second part of my vector. Yeah, I hope it's easy to see. Yeah, so it's when you look to 2 times sh, it will be 2 times h1 minus I equals, sorry, wrong projection. So it will be this one. I just used the reverse formula. Sorry. So it will just take, so when you apply this vector to h1 plus ih2, it gives you h1 minus ih2. And then you sum up with h1 plus ih2. And therefore the h2's cancel out. So you get 2h1 and you cancel with the 1/2. So gives you h1. Okay. It's not a orthogonal projection, okay? So by this, by calling it a projection, I just mean that p squared is equal to p. Same domain, same operation, yeah? So p squared equals to p. Not true that p star is equal to p, okay? So not orthogonal projection. Also not defined everywhere, so not even a bounded projection. Okay, so that's defined only on a dense set. So that's why I was telling you that like closed operators, projections, and dense domains. So those things are relevant in here. So you cannot escape of that. And I will just prove that P is closed, and the sum of a closed operator with a bounded operator is closed. Yeah, so that's basically I just can reverse this and say that sh is just 2p minus 1. And if I prove that p is closed, well, 2p is also closed, and a sum of a closed operator with a bounded operator is closed again. Therefore, proving that sh is closed is the same thing as proving that p is closed. And the proof, if you just wanted to do directly with h, is basically the same. Okay, so for proving that this projection is closed, I should look to what happens to sequences. So let h1 n plus I h2 n be a sequence into the domain which converges to a vector. So h1 n plus I h2 n converges to some vector x, which is just in the Hilbert space. Yeah, not sure where it lives. And so the second part of the, or maybe I can just put the two together like this. And I know that P of this thing also converges to some vector y belonging to H. Okay, but allow me to now use the fact that I know what P does into this sequence. So it just gives me H1 of N. Aha, okay, now things are getting more interesting because if I have a sequence H1N which lives into H converges to Y, I just discovered that y lives into h. Yeah, so that implies that y, which is the limit of something that lives into, oops, h, oh, sorry, n to infinity of h1n belongs to h, straight one, because h is closed. Yeah, so it's a closed space, which means that any limit leaves, any sequence that converges, the limit lives into h itself. So y is in h. Okay, but now what happens to x minus y? I think that's the one I want to check. So this is the limit of, okay, maybe I want to just give a little bit of space. So what is x minus y? Well, this is the limit when n goes to infinity. And now let me put all the limits together. So it's h1n plus I h2n. So this is the limit of this one is x. And then y is just the limit of h1n. Well, then this is the limit of I h2n when n goes to infinity. And therefore, this is just I times the limit when n goes to infinity of h2n, which leaves into IH. Okay, so what I learned about x, well, x is of the form y plus I x minus y. So let's just adjust the i's. Okay, maybe. Oh no, that's it's already in the way I wish. Plus x minus y. Okay, don't put no need. I would have to put two i's. It's not needed. But this one belongs to h, and this one I just learned it belongs to IH. So x belongs to h plus IH. And what is h plus IH? This thing here is the domain of SH. Okay, so one thing I read good, so I can calculate what is S of X, and I just learned that S, oh, sorry, no, not S, it's P. It's also the domain of S, but it's also the domain of P. Yeah, so the domains are the same. Yeah, so now I can calculate what's P of X. And P of X is, well, it's a P of Y plus X minus Y. And remember that P was the projection that takes the YH part and takes it out. So this is just Y. So P of X is Y. And therefore, I have exactly what I wish to have. Yeah, so I have a sequence in the domain such that the sequence converges to some vector and the operator acting to this sequence goes to another vector in the Hilbert space. And I conclude that the limit lives in the domain of my operator, and the operator acting into the limit is equal to the limit of the operator acting into the given sequence. So therefore, my P is closed. Which happens if and only if SH is closed. just because of the formula that relates the two by multiplying by a scalar and sum up identity. Yeah, so that's, as I mentioned, the sum of a closed operator with a bounded one is still closed. With a closed, it's not true. Yeah, so the sum of two closed operators is not closed, but the sum of a closed with a bounded one is. Okay, so my SH is closed. And let's try to check what happens with the other operator. So one thing that one should be very careful about unbounded operators is that two operators coinciding into a dense set do not imply that the two operators are the same. Yeah, I'm going to mention that, I hope, today into a second, or at least a big example of that. But so having the two operators coinciding to a dense set do not imply that the two operators are the same. So for unbounded operators, a set in which if the two operators coincide implies that the closure of the operators is the same is called a core. So here there is a little bit more delicate situation. And the question, okay, so that would be maybe defining a new projection, which is not given by P or by the S, but it will be 1/2 of S0. Maybe defining P0 is more suggestive. Minus identity. Yeah, so it's basically the same type of projection that I defined with SH, yeah, so 1/2, oh, it's a plus. The same type of projection, but now with a smaller domain. Yeah, so that's so they do exactly the same, but they are not the same, just because the domain is different. Yeah, so that's that goes from well, A S A omega plus I A S A omega into the Hilbert space. And when you act with a vector of the form h1 plus I h2 gives you exactly the same thing, or minus. And therefore, P0 is contained in P. So P0 is definitely closable. Yeah, because there is a closed projection which contains P0. So S0 is in fact closable. But my claiming is that, so claim is that P0 bar is equal to P. Yeah, so if you take the closure, it gives you the same. And how do I prove that? And it has to do basically as taking well, there are many ways of doing that, but basically telling what the closure has to do. Yeah, so since so the closure, remember, is the smallest closed extension. So if I have a sequence H1n converging to H and buff lives into H, of course. Yeah, so I have a sequence, sorry. No, that's the notation was correct. Yeah, so I have a sequence of elements H. Well, I don't need the one here. I just work with one. So a sequence of elements in my standard subspace converging to something that lives in my standard subspace. Let's just check the chat. Shouldn't P0 just... Oh, thank you, Pedro. Yes, so I'm thinking about S all the time. And yes, so this should just erase the first component. So it do exactly the same thing, just into a smaller domain. Yeah, thank you. Yeah, so if I have a sequence of HNs converge to a vector H, which lives in my standard subspace, so I want to show you that there is no other way of defining the closure of P0 that not saying that P0 is equal to H. Yeah, and it has to be. So notice that, so if, maybe, then, and that's the magic of the projection. So P0 acts into Hn will also be Hn because of the definition above. Yeah, because here, oh, sorry. No. So it's Sa into omega. So it will converge to something in the standard subspace. By the definition above, this projection just gives me Hn by definition, and we know that it converges to H. So out of this conclusion, I will conclude that like a P0 bar in H, oh, sorry, yeah, so H, so, and hence we have Hn going to H and P of Hn going to H. So, 0. So if I'm looking to the closure of the operator, which I already know it's closable because it is a subprojection of a closed projection, then the P0 bar has no option as having H into the domain of P0 bar and, oh, sorry, belongs to the domain of P0 bar, and P0 bar of H should be H. No, the bar was in the right place. Yeah, because of this thing here. Yeah, so that implies that P0 bar has as domain, so the domain, or like H, belongs or is contained into the domain of P0 bar. Analogously, you can say that IH is also contained in the domain of P0 bar, just by exactly the same argument. And that implies that P0 bar has to be defined into H plus IH, and in that situation, it coincides with P. Yeah, because it takes the vector and cuts the first projection. Well, therefore, since the closure is the smallest closed extension, it implies that they are the same. Yeah, so P0 bar, it has to be at least defined in H plus IH. And if you restrict to that space, it do the same thing as the original projection P. But the P was already an extension of P0, which was closed. And since the closure is the smallest closed extension, they should be the same. So what I learned is that I know exactly what is the closure of S0. So S0 bar, therefore S0 bar is equal to SH. Yeah. So I know exactly how those operators work. So I will just take these last 5 minutes. I will even maybe finish 2 minutes earlier in case Bruno is around because I am in debt with him for the 5 minutes yesterday. Just to mention the following interesting information. So we saw that by azotony, we have if a region O1 is contained in O2, then the algebras should be contained one into another. Okay, but we also learned that the vacuum is cyclic and separating for buff. So I can define this O1 omega and they take the closure, but I can define also H2 to be a O2 omega bar or self-adjoint. Yeah, so only the self-adjoint ones. Self-adjoint ones. Yeah. So those are standard subspaces. Therefore, I have Tomita operators associated to them as H1 and as H2. But notice the very interesting fact that H1 is contained in H2, just because the algebra is contained one into another. So the Tomita operators are also an extension one of the other. So what I telling you with that is that you see that the two operators coincide. So as H1 in every vector of the form H1 plus I H2 is equal to this other operator in here for all H1 and H2 into H1, which is dense. Yeah. So these vectors here form a dense set. So you have these two dense, like these two operators coinciding the two dense sets. And since H1 and H2 are not the same, so I don't expect them to be the same. Yeah, so they are standard subspaces associated with two different regions. Later, we are going to see that, in fact, it cannot be unless something strange is going on. These two operators can not coincide, and therefore coinciding to a dense set does not mean that the two operators coincide or the closures coincide, and definitely not that you can boundedly extend these two operators. So most of the times, these two operators, S, even though they are just complex conjugations, they are very badly behaved as bounded or as operators. Yeah, so they are not bounded operators. So they are closed. Thanks God, at least one of the good properties hold. But it's not true that they are bounded. Most of the cases they are not bounded, and the only situation, so SH is bounded if and only if H plus IH without the closure is already the whole Hilbert space. Yeah, that's a consequence of the closed graph theorem. Okay. With that, I finish for today. Is there any question for this last 1 minute, or maybe I should pass the word like the presentation to Bruno? Okay, no questions. Thank you. And Bruno, I will just pass you the host.
All right, thanks, Ricardo. I think this time let's remember to stop the recording and restart it just to make it easier for YouTube upload it later on.